Good afternoon, everyone, and welcome to the 2017 Chancellor's Health Policy Lecture. I'm Claire Brindis. I'm the director of the Philip R. Lee Institute for Health Policy Studies. And this series was initiated really with the drive of Dr. Stephen Schroeder, who helped, at the time, Chancellor Mike Bishop recognize the importance of health policy topics and how it intersects with the UCSF campus, whether you're a medical student, a resident, a faculty member, another type of researcher. Health policy impacts all of our worlds. And given the complexity of today's world, we thought it would be very important to have a health policy lecturer this year who may not be in the area of health policy per se, but bringing in his insights and perspectives having to do with the new innovations that are taking place in the Bay Area, and that maybe we need to think about innovation and how that affects health policy. Before Hal Barron is introduced to you by our Chancellor, I wanted to honor Sam Hawgood, who is our Chancellor, who began his career at UCSF in 1982 as a research fellow, and he then has progressively established his incredible international career in the field of pediatric neonatology research. As many of you know, he was dean in the School of Medicine and vice chancellor for medical affairs before he became chancellor. And previous to that, he was my chair as the chair of pediatrics. Dr. Hawgood is a member of the National Academy of Medicine. He is also a member of the American Association of Physicians. And he has maintained an active research practice until he became chancellor. Under his leadership, the school has really grown dramatically, and as one of the top medical schools in the country. He is also responsible for overseeing the entire $5.45 billion industry, which is UCSF, in our enterprise. And it includes the top-ranking schools, not only in medicine, but dentistry, pharmacy, and nursing. And I want to say a particular thanks to Sam, because over the last several decades, he has recognized the importance of health policy and how it intersects not only with the work that is done by researchers within the Institute, but how it really reflects all of the activity across all of our campus. So, Sam?
Thank you, Claire, and good afternoon, everyone. Not just those of you who are in the room, but those of you who will watch our speaker's lecture later online and on video. It's a pleasure for me to be here this afternoon, to be with you as Claire and her team continue to bring outstanding health policy leaders to UCSF to provide a wide range of different perspectives on current health policy issues and highlighting the important role that health policy plays in the lives of our faculty, our fellows, our residents, and our students. You don't need me to tell you that the current climate, the current environment makes it feel ever more important as we face challenges in this area. And I'm just totally thrilled and, in fact, buoyed and energized by the work of those of you who are in this room today and our leaders in the health policy across all 4 schools in the graduate division who work so hard to ensure that we continue to have a framework for healthcare that is unbiased and is breaking down roadblocks to restrict services to those in need. And I would like just to go off my talking points here for just a second to thank Claire for her vision and for really suggesting to the campus that we do something special last Saturday to coincide with Earth Day and the March on Science. And Claire really provided the intellectual framework for what was an incredibly successful and energizing day on Saturday. I don't know how many of you were able to join us on the Mission Bay campus, but we had a very successful teach-in that brought about 200 people to hear some of our faculty who are working at that intersection of science and politics, science and policy. And then we had a rally for science that was co-hosted by UCSF, the Gladstone Institutes, and the California Life Science Association, with many of the biotech community joining us on the Mission Bay campus, and Cynthia Kenyon, a prior faculty member, now a colleague of Hal's at Calico, made some very impactful and uplifting remarks at that rally. So thank you, Claire. Your vision, I hope we nurtured it, and it was very, very successful. So now it is my pleasure to welcome our speaker for 2017, Hal Barron. For the few of you in the room who do not know Hal, he is seen as one of the most respected clinician scientists and successful drug developers working in the biotech industry today. And when I say that, I don't just mean in the Bay Area, I mean nationally and internationally. Maybe we can take a little bit of credit for Hal's success, as after his receiving his Bachelor of Science in Physics from the Washington University in St. Louis, he got his medical degree from a small East Coast institution, Yale, but then had the good sense to move to UCSF, where he completed his training in medicine and cardiology here, and he continues to be a great supporter of UCSF and has an adjunct professorship in the Department of Epidemiology and Biostatistics. Hal joined Genentech as a clinical scientist in 1996, and he quickly moved up in the ranks at Genentech, became the chief medical officer and the head of global product development at Genentech. While he was there, he helped blaze a path for particularly cancer drug research that resulted in numerous new therapies that brought forward to treat all types of disease, but particularly new paradigms in biopharmaceuticals. Hal is now the president of research and development at Calico, where he is working on the mystery of aging with the goal of enabling all of us to lead longer and healthier lives. And I know we all wish Hal great success in that particular mission. But as a lead at Calico, he's continued the very strong affiliation, collaborations with many of our faculty and students at UCSF. In fact, when you go down to Calico and look who's working there, it looks like a miniature UCSF. So please join me in welcoming Hal Barron as our Chancellor's Policy Lecturer for 2017.
Well, thank you very much, Sarah, Sam and Claire, for inviting me. When Claire first asked me to give this talk in health policy, I was a little shocked because I probably know less about health policy than most of you in here, but her rationale she described was that exposing people to a different way of thinking might actually lend some innovative thoughts for people who spend a lot of their time thinking about health policy, and I thought that would be an interesting challenge to take up. So I agreed, and about a month ago, Claire and I met, and we took a little walk around her office in Laurel Heights, which I'm sure she's done before, and we mapped out how maybe best to approach a talk like this for all of you. Okay, so let's go. So in preparing what I thought I'd do, first of all, Claire gave me her book. I read quite a bit of that. I did some research on health policy to try to educate myself on what's going on in the department. And I looked back at some of the last lectures that have taken place. And I must say, I learned a lot from these videotape lectures. And I really was taken by Mitch Katz's talk from 2015. Many of you might have been there for that. I don't know Mitch well, but his talk was outstanding. And what Mitch talked about, and I want to highlight, was a passion he had for reducing the rates of HIV infection among intravenous drug users. This is his intense passion. He really cared deeply about solving this problem. And he made an observation that he shared with the group, and I'll call it a signal from now on, but an observation that was interesting. And it wasn't an observation that he actually generated the data for. He just read about it. And that was that cities with needle exchange programs have a lower rate of HIV infection among IV drug abusers and their babies. It wasn't unique, it wasn't novel, but it was out in the literature. But the challenge he said he faced, and I just quoted from his talk, so it's a little jumbled, but it makes the point that the challenge that he faced, he says I faced, is how can you publicly fund something that is an illegal activity? But if you could save lives. So Claire and I talked about the role of innovation in health policy. We weren't clear where innovation fits in. Within 10 minutes of this talk, it seemed, wow, The guy's passionate about a problem. He's made an observation that others seem to have ignored, missed. I don't know why they didn't see it. It was actually all throughout the literature. Conveniently, a very inconvenient fact, because solving it, I don't know, maybe he thought he'd go to jail. But he knew if he did, he'd save lives and really make a big difference. So I want to highlight that and talk about how I think that relates to some of the innovation I've seen. And I also want to just mention another point that he made that I thought was really profound. Again, probably escaped some, but he said to do great work, you don't have to have any good ideas. You just have to implement other people's good ideas, and the world is full of good ideas that have yet to be implemented. Seems pretty simple, but I want to get back to this at the end, because I think this is another maybe lesson that I've learned and one that I can impart some examples for. So here's my talk. Running a little late, so I might skip something, but the key thing that I wanted to highlight is a lot of innovation comes from having an idea you care deeply about, and we'll get to that at the very end. But once you have that idea that you care deeply about, the one that if you are successful in solving, that you will, as Steve Jobs used to say, make a big dent in the universe. Once you have that, I think the way to be innovative in solving those kinds of problems is to see signals. I've taught well at UCSF that it's all about the data. And sometimes the data in front of you isn't well interpreted. But seeing signals, I think, is the beginning of innovation. And I'll talk about 4 ways that I think we can do a better job at seeing signals in data. By noticing things that have either been, that have not been noticed or conveniently ignored, kind of the example I just gave, looking for what I'm going to call outliers or bright spots, or what in health policy is sometimes called positive deviance. Now I have a fair amount to say about that. I think this is a really interesting technique for seeing things that others have missed. I'll talk briefly about the idea of stressing systems to see signals. Sometimes our bodies are very complex, and a lot of times the data that we generate is in a static state. And we might not be able to see the signal until we perturb it a little bit and see how the system, the human, whatever organism you're working on doing research, or whatever system you're working on, how does it respond to that little nudge? And then lastly, and I think maybe this is the most important of all, is that you can see sometimes signals that others couldn't see because you've invested heavily and advanced the technology that allows you just to see things that just didn't exist before that technology became available. I'm going to talk a little bit about what you do once you see these signals, you act on them. I like this positive deviance model. I applied not just to data, to outlier points, but to companies, to institutions. There are some pretty exceptional places like UCSF, and the question is why? What can you learn from these outliers, these groups? Like, I'll argue Bell Labs is quite unique. And I'll mention some of the things that I think led to that. Taking the long view, the importance of cognitive diversity, seeing orthogonal views to help solve a problem, and then making little bets, small, affordable ideas that you might want to take forward and kill when they don't work, but that can enable you to iterate, and then maybe you see the aha moment and you make it happen. And then lastly, I want to talk about inspirational people solving aspirational challenges, because I've had a very, very unique experience in life, and I've gotten to meet quite a few amazing people, some of them here, and just a few things I've learned from them that I think enables innovation. So that's the outline. So seeing signals, I thought, I know nothing about sports, and I have to be careful about showing anything that's sports related, but I thought this was interesting. So this guy, Dick Fosbury. I don't know, how many people know who he is? Oh, good, not too many people. So I didn't really know who he was, but he was born in the late 40s, and he's an American retired high jumper who was considered one of the most influential people, athlete in the history of track and field, because he won the gold medal in 1968, revolutionizing the event with the so-called Fosbury flop. Okay, people used to jump over in what might be a more intuitive way, like kind of jumping over, and I want to show you a video, and I want to tell you what I experienced from that video.
The 1968 Olympic Games proved to be a turning point in the history of the high jump event. Into the Mexico City Olympic arena came not only a new name to the sport, but a new approach, which was to revolutionize the high jump event. Dick Fosbury from the United States demonstrated a new style of high jump, which some considered strange and awkward. It was a jump he had devised in the previous years, and one which unsettled his opponents. While the crowd at first saw him as a novelty, his continued success at clearing the ever-increasing height soon made it apparent he was a serious contender. Valentin Gavrilov from the Soviet Union, failed at his attempt of 2.22 metres, while Fosbury and his US teammate Edward Carruthers cleared their way to a jump-off. The bar sat at 2.24. Carruthers failed, and Fosbury took his new style of high jump over the bar and into the history books. Fosbury had won his gold. Within a few years, the Fosbury flop had become the standard method of jumping in this great Olympic sport.
So to me, what was interesting about this is two things. First of all, if you do the physics, this is way, way better idea. It's not even close. The center of gravity shifts in a way that anybody who thought orthogonally about how to get over this bar and happened to have a physics background might have said, well, I have an idea. The second thing that was interesting is Fosbury wasn't the best at this. He was stuck at 1.5, and he had to think about an innovative way. He was passionate about winning a gold medal. He wasn't going to do it without an innovation, and he found something. But he actually didn't find it through the physics. It turns out, and in fact, when he was practicing this, all his coaches said, this is ridiculous. But he saw something that no one else saw. He probably didn't even notice it. But he landed kind of on his neck, okay, which is no big deal if there's a rubber mat, which there was. For the last, I think the Olympics started in 1896 with the high jump. And for the next about 70 years, 65 years, it was a sand pit. You can't land on a sand pit on your neck or you'll be visiting UCSF. So it wasn't possible. But sometime in the mid-60s at colleges, rubber mats became available and they thought a better idea. But people for 70 years hadn't noticed that the best way isn't to go over, but it wouldn't have mattered because they would have hurt themselves. But when the rubber mat came, and it was there for a good 4 or 5 years before anyone noticed, that it enabled you to think about an innovative way that everybody else didn't notice. There was the mat. And so a theme that I want you to leave with is there's rubber mats running around all over the place that I don't think we notice, and I bet there's one in health policy. Think about what it is that everybody can see, you can see, and you haven't noticed, that it will allow for an innovation if you care deeply about your problem. So that's sort of an intro. I've spent a lot of time, maybe about 17 years at Genentech, thinking about how to innovate. And one of the lessons that I want to talk about beyond sort of noticing things that other people have ignored is how this can apply to medicine and science, and particularly in drug development. One of the interesting stories that I got to be involved in at Genentech was we were pretty sophisticated understanding of the HER2 biology from development of a drug called Herceptin, which blocked the HER2 receptor in women who had overexpressed that receptor for breast cancer, and it had some pretty dramatic results. And we thought we'd leverage that understanding of the HER family biology to look at another pathway that's related, and that's the EGFR receptor. The EGF receptor is HER1. And we had really understood HER1, HER2, HER3, HER4, and we thought that based on the biology, this was a very likely candidate for causing growth and differentiation of cancer cells, and we thought that inhibiting that might be a good idea. But what seemed interesting from the data, unlike women with overexpressed HER2, overexpression of HER1, the EGF receptor, didn't seem to predict who was going to benefit. So the studies were done in all comers. And the first study to unblind was actually a revolutionary study. It was really, really difficult to see a survival advantage in lung cancer. But Tarceva, this EGFR inhibitor, was studied in third line, which means in patients who had been refractory to existing chemotherapy. They had no other options. And in fact, compared to placebo, in this setting, there was a 30%, a hazard of 0.7 survival advantage. And this was a big advance in oncology at the time. The inconvenient part was that very soon after, pretty much at the same time, the earlier study in the more frontline patients, on top of chemo, the other one was by itself, didn't work. And if anything, if you look early on, it almost looks like it's worse. But the hazard of, it's essentially absolutely no effect, 0.995. Wow, what's going on? And this was shocking to people because clinicians had been treating people with these drugs. They said, it's hard for me to believe because I've seen patients who have these very quick, rapid, dramatic responses. I know it works. That doesn't happen. We say, well, I don't know, it doesn't happen, but it doesn't work. So what's going on? So some people back at Harvard, this is back before all this became very standard, said, well, wait a minute, let's look at these outliers. There's about 10% of people who have these dramatic responses. What's different about them? And so Tom Lynch actually hooked up with a colleague of mine, Jeff Settleman, who's now at Calico, and said, hey, can you sequence these patients' tumors and tell me why they're so unique? And it turned out that these patients had a mutation in the EGFR receptor that made it fire all the time. Those are the patients for whom that cancer really is being driven by this pathway, and for whom one might have even expected a very, very rapid and robust response. So with this knowledge of these outliers, you can actually start understanding the biology of drugs that were even being developed for a different reason. This wasn't even known when this drug was being developed. And what's amazing about learning about these outliers is the next step, which is to say, even though it didn't work in the frontline setting, which is where most of the patients could benefit, let's restudy it, but only in these people. And let's not just see if it's better than placebo. Let's go against standard of care. Let's go against the traditional chemo these patients would get. Because this should tell you that the chemo is not the right regimen. This is. So we designed that, implemented it, and this is a shocking result. This is in the population where there was no benefit. And now it's no benefit. It's not compared to placebo. This is compared to active therapy, chemo. And there's a threefold almost improvement in progression-free survival because we selected out these patients who had this unique phenotype, this unique genetic makeup. And we learned that from these outliers. They taught us about the biology of the disease, where the therapy could use, and this is not standard of care for this population. This isn't just unique to oncology. This is a fun example. I don't know if anybody knows what this is. This is a Grasshopper Mouse, which is interesting to me because it's an unusual mouse. It lives in the desert where there's not a lot of food, but it's evolved to have a very unique feature. Out in the desert, there's not a lot of food, but there are scorpions. But nobody eats scorpions because they're very, very, very painful when they bite you. The grasshopper mouse doesn't seem to care. It can eat a scorpion in a couple bites and doesn't even flinch. And in fact, you can study that by injecting the venom into a regular mouse and this grasshopper mouse, and it doesn't fire the nociceptive fibers. It doesn't know it's painful. And so it's evolved in a very special way. Okay, interesting. What do we do with that? Well, turns out there are people who have mutations, very rare, and these people are called congenital insensitivity to pain, CIP, and they also have an abnormality in a sodium voltage gated channel called NaV1.7 that's missing. This is how you sense pain. Just like in the grasshopper story, the grasshopper was unable to sense pain because it had a mutation in the NaV1.7 and NaV1.8 pathways. This exists in humans, very rarely. And what this experiment of nature has told us, they're pretty fine otherwise. They don't have any pain. I mean, you can, they can break bones, they don't notice. They can have they can even have childbirth. I mean, they don't experience pain. So their life is very challenging in many ways. And this is certainly not a blessing in any way. In fact, they have lots of accidents and tend to die of accidents, so it's a terrible problem. But it's a clue about how we might use these very, very rare species, the mouse, the grasshopper mouse, and humans, to imagine developing an inhibitor of NaV1.7 that might be a tremendous benefit for pain control that's not addictive, non-opioid, and transform medicine. Let me give you a couple more examples. This is one that I enjoy being a cardiologist. Back, I don't know, maybe 20 years ago now at UT Southwestern, Cohen and Hobbs made an interesting observation. There were some people in their clinic that were having phenomenally low LDL. What's going on here? They're outliers. Started learning about the biology, and it turns out that there's a protein that we all have called PCSK9. You probably heard about this. What this protein does is just to back up, the LDL receptor sits on cells, and as LDL floats through your body, it grabs the LDL and processes it, and the LDL receptor lowers your bad cholesterol. That's a good thing to have happen. PCSK9 blocks the LDL receptor's ability to do that. So PCSK9 increases the bad cholesterol and causes problems. But guess what? Not surprising, there is about 1 or 2%, depending on your ethnicity, of people who have a mutation in PCSK9. It doesn't work. What happens? It doesn't bind the LDL receptor, and therefore, LDL receptor does a better job than it would normally do. Cholesterol goes down, and guess what happens to these people with these mutations? They have much lower LDL, as you might expect from the biology I just described. You can see that on the bottom. These are the mutated variants in the genetic makeup of the protein relative to non-wild type, the normal. But what's interesting is they have about a 90% reduction in cardiovascular disease. And you might say, good news for those people. But again, what about just making an antibody to the protein to mimic the genetic condition? Right? So you could just, again, think about, and that's actually been done. So you're probably familiar with this, but this just came out in the New England Journal a few weeks ago. This is the culmination of a lot of work. And this is the name of the antibody that blocks PCSK9 and the primary endpoint of a cardiovascular study. It's been a long time since this has been such an advance because the therapies today are pretty good, but this still had about a 15% reduction in the primary endpoint major adverse cardiac events. And in fact, when you look at the secondary endpoint, which is actually the really serious ones, it's actually working even better. Again, we can learn a lot from these outliers and develop therapies for the general population. It teaches us a lot. It's not always that easy, though, and I thought it's always good whenever you propose a new idea to show why it might not work, because there's two reasons, there's plenty of reasons why it might not work. I'm going to give you two. This was a really exciting paper about 5 years ago now in Nature that resulted from analyses of the Decoding Project. This is a project where almost the entire population of Iceland has been either directly or indirectly sequenced. And they're a unique population because you can actually trace, I think, almost every Icelander back to a founder. So you can impute a lot of genetics. But in any event, what they found was in a very rare number of people, about 0.5% of the Icelandic population, they had a mutation that seemed protective. What was the mutation? This is just, again, 30 seconds biology. One of the predominant views, maybe not as predominant as it used to be, but one view about Alzheimer's is you have this amyloid precursor protein, APP, and it's shown in the middle there. And it can get cleaved off the cell membrane by either, on the left, gamma secretase, and it cleaves it a little bit lower because it recognizes an amino acid sequence, it's a protease, or it could be cleaved by beta secretase, a different amino acid sequence. When it's cleaved on the left by gamma secretase, it doesn't form amyloidogenic plaques. There's no amyloid buildup. You don't see the plaques that you commonly see with Alzheimer's. When you clip it with beta secretase, you do get the plaques. And what's interesting about this mutation and why the story seems so exciting is these people have a mutation right where beta secretase recognizes the amino acid sequence to clip. So they can't clip. So they have to go through gamma secretase, and therefore they don't build up the beta amyloid. And these patients have less beta amyloid when you image them. And so companies said, well, I got an idea. I'll make a BACE inhibitor, beta secretase inhibitor. You know, there's challenges, I won't go through that, but years later, there's a beta secretase that's reasonably safe and gets into the blood, crosses the blood-brain barrier. And in fact, in phase 2 studies, it looked like it's clearing amyloid. So, wow, maybe this is a massive breakthrough. Well, I was using this as an example of what I'm excited about until a few weeks ago when I read, to my surprise, that Merck pulled the plug on the phase 2/3 BACE inhibitor program because a DSMB met and said there's essentially no chance that this will work. And I thought, wow, how could that be? But if you think about it, one of the liabilities of this genetic model, it's a strength, but it's a liability. This BACE inhibition, if you will, that these unique people had is from birth. They couldn't make APP process through BACE from the day they were born. This was given for, I don't actually know how long it was given for, but it's probably on the order of months to years at the most, in a population that had clinical symptoms. Maybe it's too late. Maybe if you had given this, and this is a big maybe, earlier on in the disease, it would have worked. And we haven't seen the data. We have no idea if there's clues for that. One could imagine exploring that data with that question. But it's interesting to note that in their press release, they say that the same doses, so it's probably not a dose problem, are continuing to be used to treat people with so-called prodromal AD. That's before the symptoms are manifest. And that might be one of their hypotheses too, that maybe earlier on. Now, wouldn't it be great if we could just identify these people so early on in their disease, before it's a disease, and treat them with something? Maybe that's going to be the only way of actually finding a cure for Alzheimer's or significantly reducing its severity. So how do we do that? It's another opportunity for signals. So there's a few cardiologists in the room. Sometimes you look at a person and in their static state, they look fine. But when you stress it, you bring out clear evidence that they're not normal. we know this from treadmill testing. You can take a person with chest pain, exertional chest pain, you get an EKG on them, it's normal. You put them on a treadmill, and you get the classic 2 or 3 millimeter downsloping ST segment depression that tells you their myocardium is not getting enough blood when they run. This is a bad sign. You can go and image them, you can go and cath them, you can find that they are fine without stress, but they can't maintain that homeostasis very well. They have a problem. We know this from endocrinology and diabetes. You might have a normal glucose, but if you get a glucose challenge, a stressor to the system, how well can you maintain homeostasis? How well is your pancreas and insulin levels able to adjust to keep your glucose low? Normal's pretty well. But there's these population that previously weren't even recognized as a disease called impaired insulin sensitivity. And then, of course, type 2 diabetes. If you actually look at their insulin levels, the impaired insulin-resistant patients have very, very profoundly high insulin. They're trying to compensate, and over time, they'll fail as they progress to type 2 diabetes. But this is a way of identifying disease way before clinicians would ever notice that they have a disease. And maybe stressing a system and looking for signals is a way to not only identify signals, but actually identify patients at risk for developing things so that we can start intervening early. And because many diseases manifest clinically when almost all the damage is done. I mean, this is sort of a theme if you see a lot of different diseases. The body can compensate pretty well. By the time you complain of something, it may be too late. But that's an inconvenient problem. But if you really want to be innovative, let's get some signals. Let's stress the system and find out how it responds. And lastly, I just want to show this woman. This is such an interesting woman. She's not around anymore, but she's the oldest person to ever live on the planet. She was French. She lived 122 years and 164 days. When you're that old, you count the days. What's interesting about her, she was an outlier, of course, right? Extreme outlier. At 85, she took up fencing. She rode a bicycle until she was 100. She smoked from age 21. She ate a diet rich in olive oil and chocolate, 2.2 pounds per week. I'll be extreme, but I don't think anyone thinks because she started smoking at 21, she lived to 122. But another way these outliers can fool you is because, and this is where I think the genetics are very, very helpful, where you don't have this problem, or at least as much, associations that are not in the causal pathway. So you have to be very careful about interpreting outliers. The genetics are nice because they're experiments of nature. They're random, basically random allocations of mutations, and you can see they're not confounded, at least as much. We can pretty much guess smoking's not a good idea. Is taking up bicycling at age 100 strongly correlated, at least living to 100, right? Because but probably reflects some other underlying biology. But also possible is if you think about distributions, biostatisticians will look at this and immediately go, well, wait a minute, outliers they're defined by a Gaussian distribution. There's two standard. Every distribution will have random noise at the tails. There's always outliers. I love this one, so I just want to quickly show you this to you, because so this is an incredible story. Richard Lustig, who shockingly person who won the lottery again and again and again. In fact, he wrote a book, Learn How to Increase Your Chances of Winning the Lottery. He won a grand prize, which I think is defined by, I forget how much money, but a lot of money, 7 times. And he wrote this book that you can buy on Amazon on how to actually do this. It's a 40-page book. Shockingly, it was the number 3rd ranked Amazon book in the bestseller in the self-help section, which I think is probably pretty big. And here's a quote. This is just shocking. Despite winning repeatedly over the next few years, Lustig didn't see that there was a pattern until his 4th win. He said, I didn't even realize I had a method until my 4th win, even though everybody else was saying, oh, you're just a lucky guy. There's no such thing as a method. He's saying, no, I'm saying I won 4 times. How can you say that's just luck? Of course it was just luck. And there is going to be somebody who wins the lottery 7 times. And I'm pretty sure he doesn't have a technique other than buying lots of lottery tickets, but in terms of a technique for doing this, so you have to be very careful that the outliers are actually telling you something real as opposed to just noise at the tails. But there's a lot of opportunity there. So the last one I want to highlight is how valuable advanced technology can be. We're living in an era that's exploding with incredible technology, whether it's genomics and sequencing, microscopy, and all the advances in physics and fluorescent probes and whatnot, or mass spec. Imaging is just getting more and more sophisticated. We're seeing things we could never see. Single cell analysis is incredible, what we can now see it in not just the whole organ, but in individual cells. And I just wanted to show you an example of this to show how powerful. And now's the fun part, there's a quiz. So this is data, gene A. When gene A is high, gene B is low, right? You can look at the scatter plot and go, well, it looks really interesting. If I want to learn how to modulate gene B, I could learn a lot from thinking about how gene A might be modulated. But this isn't a tissue, it's an example, where, let's say it's the kidney, where some of those cells are glomeruli. Some of them are mesenchymal cells and collagen, and some of them are going to be thick, ascending limb, and some distal tubules, whatever. They're going to be cells from all over the kidney. If we actually could measure the transcript levels in each of the cells, we might observe something like this, where our conclusion that the correlation exists as it does on the left, where high A equals low B, could actually be completely wrong. And what's bizarre about this is that in the aggregated population, high levels of A lead to low levels of B. But in each of two subgroups that makes up the entire data population, the opposite is true in both. So, if you're an epidemiologist or biostatistics, you have to answer two. Does anyone know what this is called? First person to raise their hand. Yes? Interaction. It's a type of interaction. What specifically type of interaction is this? Okay. Now the biostats, maybe you only need one. We have a biostatistician. Okay, well, maybe I think about a second question, but this is called Simpsons Paradox. And I remember first learning about this from Warren Browner, who to me was one of my greatest mentors at UCSF and always stressed the importance of looking at data. And when I heard about this, I thought this is impossible. How can you have an effect in the aggregate data set that suggests, let's see, what would be a good example, that sugar is bad for you in the aggregate population. It's associated with increased risk of cardiovascular disease, let's just say. But when I looked at men, it was helpful, and when I looked at women, it was helpful. And you want to say, hold on a minute, there's not a third group. How could it be helpful in men and helpful in women, but harmful in the aggregate population? And it's a fascinating example, and I think probably not uncommon, that the Simpsons Paradox can exist for this exact reason. It's the same data, where you can be misled because you don't have this advanced technology to be able to see deeper into the data you're using. So you can see a lot of data by advancing. And the last one I want to talk about is one I think might be, maybe, the most important one for health policy. We are living in the Bay Area where you can't go anywhere without hearing about machine learning and artificial intelligence and the massive advances. And I remember, when is this from? I think this was about 4 years ago. I remember thinking, how does Amazon do this? How do they get the packages to me so quickly? And one of the tricks they figured out is by looking at your patterns, they can actually predict when you're going to buy something before you know you're going to buy it. And you think, well, how can they know before I know? I mean, I'm in charge. Okay, I know it's a weird thing, but they seem to know before you know. And it's because they're looking at lots of data that you might not be processing accurately. And this is going to be more and more true of these massive, massive big data sets we see, is we can't see, they're too complicated. There are patterns in there that humans can't even begin to be able to see that computers can see instantly. And you know that they're there because, for instance, in radiology, when you've been doing it for 20 years and you show something to a really, really seasoned radiologist, they go, I think, they don't have pneumonia, but I think they might have Paget's. Or, they see something. And you think, wow, 100 people looked at this. How did you? They see things. Well, computers can do that after training in an incredibly short period of time. And they're going to get better and better and better. And I'm wondering if there's not a lot of massive data that's being generated that is going to completely transform how we think about medicine and maybe most fields because we leverage this technology. And I know you have a tool coming here now, and I would love to think about how he and machine learning and some of these advanced technologies can be employed by health policy, other places that you see to come up with really significant advances. So our bodies, we all know this, they're very, very complex. It's an ever-evolving network. We draw these pathways as if they're linear. These are networks that are dynamically moving and responding to perturbations. It's too complicated. But these technologies are allowing us to see things, and the machine learning and artificial intelligence is allowing us to deconstruct these patterns in ways that we're going to see things that are not only incredibly valuable, but wildly surprising and probably allow us to really rethink a lot of what we think we know. Let me tell you this example, because this is really fun. So how does all this positive deviance, this outlier stuff relate to health policy? I wanted to tie it back in some way. So I started looking, is this, fine, this is great for drug development, but that's not what you do, and maybe some of you don't even care about, but this is an interesting example. So in 1990, this guy, Jerry Sternin, was sent by Save the Children to fight severe malnutrition that was clearly endemic and incredibly problematic in Vietnam. And at the time in Vietnam in 1990, the United States was not helping with this problem, probably causing a bit of this problem. And so they were very cynical about people from the United States coming over to solve their problems. So they invited them, they let them come, they were very cordial, but they said, you have 6 months to solve malnutrition. So he says, well, 6 months, okay, at least. And he was well-versed in all the academic sort of, causes, poor sanitation, poverty, lack of education, et cetera. But in 6 months, he's not going to fix these. So what does he do? Well, he does something really interesting. He goes there, assembles a team, and he just goes out in the villages with the question, are there families where, despite having the lowest income, malnutrition does not seem to be anywhere near as much of a problem as you might expect? Are there outliers? So they took this team out, and in actually a period of a month, they actually came back with the data and said, there's some definite outlier families. It's not clear what's going on, but they don't have malnutrition in these villages. So they said, okay, let's go study those. So they went out there and they started interviewing these moms and families and say, what are you doing differently? Good, it could be random, but looking for signals. And what they found were two things. First, these mothers would routinely say, well, I feed my kid 5 meals a day. One typically before I go out to the rice paddies, and one when I come home, which was the conventional wisdom. Most kids got 2 meals a day because it was convenient before and after they left. These mothers would say to whoever's taking care of the kid during the time they went to work, the brother or the grandmother or somebody, please feed them 5 meals. But they only had enough food for 2 meals. So they didn't get more calories. They just got smaller amounts of food 5 times a day. Just a fact. And the second thing they said they did is routinely take the brine shrimp from the rice paddies that no one uses because it was actually thought to be either a sign of being extreme poverty, the lowest of low class, that no one would admit to doing. Or in some cultures around there, it was actually considered toxic. Like you wouldn't want to eat these things. But they took the brine shrimp, and they also took the green part, the top part of the sweet potato plant that was planted endemically around there. And they cut off the green part, which is always thrown away, and they added both those to the soup. And they made sure when they served the kids with the ladle, they would get down to the bottom and get all those things for them. 2 things. And what they then decided to test was whether that was true and unrelated, an association that's like chocolate, or I shouldn't say that, maybe that was the cause of her longevity, but something that might have been unrelated. So what they did was yet another unique thing. They noticed these women had a solution. They asked them to go to the other villages and teach. Teach what you do. Show them how you do it. So he helped them teach. And in the 6-month period he was there, 65% of the villages that he intervened on with this essentially helping people who already knew the answer, 65% of the families had a reduction in malnutrition. He just captured the positive deviance in their techniques and leveraged it. And it gets back to what I think Mitch said so brilliantly. There are a lot of really good ideas out there. You don't need to think of them all. Just find them and make them happen. And you can be very, very, very innovative and save lives with just asking people what they do. You can see this positive deviation in companies. I think Bell Labs is one of the most interesting companies ever. During its 50-odd years of existence, it was one of the most productive, maybe the most productive scientific laboratory on the planet. The folks at Bell Labs during this time period won 8 Nobel Prizes. They contributed to incredible ideas that have changed dramatically how we live. Almost everything we do is a result of something that came out of Bell Labs, such as the transistor in 1947, the computer using the transistor in 54, solar batteries, charge coupled devices, which basically were the beginning of digital photography. They had fiber optics. They even did programming languages. They developed Unix, C. They did Six Sigma. They were doing incredible stuff. Now, how did that happen? Because this is a little place in New Jersey that's in a pretty boring building with a bunch of smart people. And there are 5 things that I just want to leave with, which is that they had an inspiring goal to create a new world, basically. They told their people, look, we want to be globally connected. We see a future that could be very, very, very different and incredibly exciting if we can connect the world. So let's transform knowledge into new products that could do that. They hired, and this is a really key point, they hired all these different interdisciplinary, they had physicists, they had metallurgists, they had chemists, they had lots of different people, all giving different perspective on how to think about problems. And they were very innovative because of their ability to tap into all these different people. I have a feeling any one group might not have ever seen how to make a transistor. In fact, I have a feeling if their goal was to make a transistor, which it was not, there probably wouldn't have been a transistor. They were just trying to network the world. They hired incredibly outstanding people and told them to be creative. Trust them. They'll do some great things. They had a long-term focus because Bell Labs actually was part of the Bell Telephone, which is essentially a monopoly, and they were spinning off tons of money. They had a stable source of revenue, and they could take that money and take a long view in trying to solve problems. It's a very unique company, but it's not possible to imagine how you could replicate that. And they did something that I want to just mention, is they took lots of little bets. They would try something, wouldn't work, move on. Try something, wouldn't work, move on. Try something, wouldn't work, move on. They didn't mind that when you take a little bet, oftentimes it's going to fail. They didn't see failure as what we might think of failure as the opposite of success. They thought of failure as the necessary steps to become successful. Got to try lots of stuff. Who knows what's going to work? But once you see something's not working, kill it. And once something is working, move it up. And this is yet another feature of innovative institutions. Lastly, I just wanted to comment on people. You said maybe UCSF played a small role. UCSF played a huge role for me personally. Probably, I'm quite confident no other institution played a bigger role. I got to meet some impressive people through a collaboration that Andy Grove did with UCSF and UC Berkeley. He asked me to chair his board, where he tried to bring together engineers and clinician scientists to think about transforming medicine. And from him, as well as from David Ebersman, who was the CFO at Genentech and became the CFO of Facebook and now is the CEO of a healthcare company trying to reinvent how we think about mental health. These two people taught me how important bringing people of different disciplines. I can't tell you how much I learned from a financial person about medicine and science. Warren Browner, I mentioned. Warren was one of my first attendings. He was someone who always said, "What's the data say? Are you sure that's what the data says? Have you looked at the data harder? Look at it harder. Look for signals. Don't be fooled by noise." And I can always hear Warren. I can hear Simpsons Paradox whenever I think. And he's a special guy, and he's doing innovative things too. Sue Hellman, whom you all know, the former chancellor here, she was my boss for over a decade, I think, and learned how important passion is about the problem you're trying to solve. Art Levinson is probably one of the most important mentors to me. I've known Art for 21 years, and he really has been a big believer that innovation occurs from advanced technologies, from taking the long view, from hiring outstanding people. But I wanted to end with just one quick story, because the most important person to me ever that I think has influenced me, well, I know has influenced me more than anyone, is Kanu Chatterjee. I'm just curious, does anyone know who Kanu was? Yeah, sort of the people. But Kanu was an amazing person. And I wish everyone got to have met him. He's brilliant, hardworking, highest integrity, humble, compassionate, soft-spoken, kind. I'm sure folks who've known him would add things. He was clearly a world-class clinician, an outstanding teacher, but by being a great clinician, scientist, et cetera, he not only changed UCSF in a way that I think is quite profound, but he changed all the people he met, whether they be students, faculty, patients, administrators, anything. He had a huge impact. And I just wanted to, he's such an extreme outlier that I just wanted to share one last story that was very meaningful to me, and I think about all the time as a leader and how to make innovation happen, is from Kanu. So if you're a resident or a fellow, you might appreciate this. When you're a resident, the very last day of residency, you're a really good resident, but if you have a specialty question, you call a fellow. The odd thing is the very last day of residency and the first day of fellowship are separated by 24 hours, and you go from not knowing what you're supposed to do to being the best in the hospital for that problem. It's a little scary. So when I went from resident to fellow, it's probably not quite that bad as when I was training, but I became a cardiology fellow, and it's kind of scary. Many of those cardiology fellows were macho, and they all wanted their first rotation to be CCU or cath lab. I was nervous, so I said, "Can I do echo?" You know, the chances there's an emergency seems pretty low, and they said, "Sure, no one wants to do echo," so I did echo. 3 weeks into it, my beeper goes off on a Sunday night, and I'm pretty sure it must be a mistake, because I'm told there are no echo emergencies. So I call back, and it's 12 Moffitt, high-risk pregnancy ward. We need an echo. I'm like, gotta kidding me? Really? My first thought was, I don't even know where the machine is. They didn't even tell me where the keys are to the echo lab to get it. So I go in, panicked. First of all, I don't even know how to use it really. I mean, a little bit. So I go in, I find the keys. I actually, back then, I wheel this massive machine up to the 12th floor. There's a woman there who's high risk, and in the note it says, make sure she doesn't have pulmonary hypertension to determine whether she should deliver vaginally or C-section. I'm thinking, oh my gosh, seeing the TR jet and getting the PA pressure is not easy. But I'm proud that I actually found the echo machine, so I go up there, and I'm looking around. I spend about 45 minutes with this patient, super nervous. I don't know what to do. I don't even think there's an echo attending because it doesn't happen. So I'm sweating. I don't know what to do. I come out of her room, and it was like a miracle. I see at the front, this is Sunday night at 9 o'clock, I see writing notes in a pressed white jacket, Kanu, Chatterjee. I'm like, what? This is like, okay, there's a God. And he says, hello, Hal, how are you? And I said, I've been better. He says, what's the problem? I said, well, there's this woman, she had pulmonary hypertension, da-da-da. He goes, sounds very interesting. Do you mind if I take a listen? I'm like, no, I do not mind if you take a listen. This is the guy who is, of course, probably the best clinician in the world, able to hear pulmonary hypertension better than an echo machine. So he comes in, examines the patient, tells me exactly where to listen, tells me how to judge the pulmonary pressures because of the P2, blah, blah, blah. I learn a ton. He says she'll be fine. We walk out. He goes, thank you. I said, thank you? And he says, is there anything else I can do? And I said, well, if you wrote in the chart she's fine, that means a lot more than if I write she's fine. So he says, I'm happy to. And he took his red pen that he always had and he wrote, she will do well. And she did well. 2 months later, I start my CC rotation, and the charge nurse, who was a friend of mine, having been a resident, says, hey, how did that high-risk pulmonary hypertension woman do? And I said, oh, she did fine. She delivered fine. Everything's fine. I said, how'd you know about that? And she said, well, they called for your beeper, and I gave them your beeper. And I said, oh. She goes, did Kanu help you? And I said, why do you ask? Because he did. She goes, oh, well, he always calls on Sunday night to find out how the patients in the CCU are doing. And I'd mentioned that since you don't really know how to use an echo machine and you got called that you might need help. And I said, oh. So what happened, I think, is Kanu came in because he knew that I probably would have a hard time bothering him, and he probably was waiting outside that room for a good hour while I was fumbling around, not knocking, going, I'm here in case. He didn't want me to feel bad. He wanted me to learn, and he wanted to teach, and he wanted to make sure the patient did well. And that was a big day for me because I realized that when you're really passionate like he was about making a difference for patients, you do what it takes. And if you do that every day of your life, when you end up leaving, you're going to leave a legacy that is going to stimulate people to do all kinds of wonderful things. And so I never got to say thank you when I left UCSF, but I feel really appreciative of getting exposed to so many great leaders like Kanu, and those experiences definitely shaped me more than anything in terms of how to be a leader. And I'll end there, and thank you.